let's talk about scientific notation. Now, that was something that some of you struggled with on the, if you took the placement test, that was one of the areas that, I don't know, maybe about half the kids that took the placement test had an issue with scientific notation. So let's do a quick refresher on that. Again, this is a concept that if you don't remember it, we don't have time, we're not going to be able to spend a lot of time on it, but it's something that you can look up at home, get your math book out, go to Khan Academy, something like that, and refresh your memory on it. So let's say that we are using a measuring device that's accurate to 1 meter. All right, so it's accurate. This is just kind of a refresher from last week. It's accurate to 1 meter, and we take a measurement and we decide that something is 50 meters. Is that the correct way to write that measurement? Based on the precision of our instrument. I'm seeing yeses and I'm seeing no's. The no's have it. This is not the correct way because our instrument, basically what this means when it's accurate to 1 meter, it means that the tick marks on our measuring device are to the ones place. All right, so every 1 meter there's a tick mark on there. And remember what we said we want to do is whenever we're using a measuring device, we want to always estimate in between the tick marks, right? And so that means we would go to one more decimal place. So if I'm going to write this with the correct precision based on our measuring device, I need to write 50 meters like that. Okay? Is everybody clear on that? That'll have some bearing once we start taking measurements with our labs and all. All right, so that tells me that because I wrote it this way, that tells me that my measuring device was accurate to 1 meter. Okay? Or was precise to 1 meter. So we see how to do that. Let's say we have this measurement, but we want to convert this measurement to centimeters. All right, so we've got 50.0 meters, and we want to convert it to centimeters. And so we do our conversion. We know our conversion relationship is that there are 100 centimeters in 1 meter. So we write that down like that, putting our centimeters on top because that's the measurement we want to end up with, so that our meters will cancel out. And that gives us a final measurement of 5,000 centimeters. Now, one of the things that we said last week is we were talking about precision and we were talking about significant figures. And we said that whenever you add and subtract, you have to worry about precision or significant figures. Anybody remember?
Precision.
Precision when you add and subtract, right? So you're looking at the least precise number. So if you're adding two numbers together and one has 1 decimal place and another has 2 decimal places, then whatever your final answer is, you have to make it go along with the least precise number. So your final answer should only have 1 decimal place, right? But with multiplying and dividing, we don't worry about precision. We worry about significant figures, right? So here we're multiplying and dividing, right? And our original answer had how many significant figures?
2.
Who says 2? All right. Who says 3? Who says 8? Put your hand down. I'm joking. No one put their hand down. 3 is correct because remember, if it's a number between if it's 1 through 9, it's significant. If it's a 0 at the end of the number to the right of the decimal place, then it's significant, right? So we know both of these are significant. And any number that's in between other significant numbers is also significant. Yes?
Does the 0 only count if it's like the last number, or if
It's got to be the last number to the right of the decimal
place? So if it was like 50.00, whatever, the first 0, well, never mind, it would.
It would, because as soon as we've got a significant one at the end, everything in between is also significant, right? So yeah, it didn't matter. It wouldn't matter how many, all of these numbers in between now are significant because this is significant and this is significant, right? All right. So does everybody understand now why there are 3 significant figures in that one? Right? Okay. So since we started with 3 significant figures, we have to end with 3 significant figures because we multiplied and divided, right? We multiplied by 100 and divided by 1. Well, does that have 3 significant figures in it? Do we have any way to rewrite that with 3 significant figures? If you do it in standard, what you call decimal notation. There's no way for me to modify that, right? I mean, the best that I could do is I could add a decimal place and some zeros on the end. But if I added a 0.0 to the end of this, now I've got 5 significant figures, which is more than what we started with, right? And we can only have 3. And so we use scientific notation to represent this in a way that has the correct number of significant figures, all right? So I could rewrite this 5,000, I could rewrite this as 5.00 times 10 to the 3rd power centimeters, okay? And now my number in the front here has 3 significant figures in it. So one of the reasons that we use scientific notation in chemistry is so that we can maintain the correct number of significant figures when we're writing our answer. Any questions about that? All right. So just to very, very quickly go over scientific notation. Remember, if we have 5,000, we always write with scientific notation, we always take the first number, and sometimes you could have the decimal or not have a decimal after it, but we would never write this, right? Not with scientific notation. You always write it with a single number, then followed by a decimal, and times 10 to some power. So how do we figure out what power we're going to write that to? Well, if I were to put a decimal place here, I would have to move that decimal place 3 places to the right to get my original number. So that's why we have a 10 to the 3rd power. All right? Now with scientific notation, it could be a positive exponent on the 10, or it could be a negative exponent on the 10, right? And so if I wrote 5.0 times 10 to the negative 3rd power, then what that means is that if I were to multiply that out and write it in decimal notation, I would have to move my decimal place 3 places to the left, making the final number smaller. So if I take my 5 here and I pad it with some zeros, and I move it 3 places to the left. So my decimal place was here, and so I go 1, 2, 3. So I would rewrite it. I'll write it down here so you can see it better. I would rewrite it like that if I wrote it in decimal notation. And so the way that you can remember, whether you're moving this decimal to the left or the right, whether you're making the number bigger or smaller, is when you look at this, 5.0, if I'm multiplying that times 10 to the 3rd power, is the final number, if I wrote it out in decimal form, is the final number going to be bigger or smaller than 5? It's going to be bigger, right? So if I want if my original number is bigger than 5, then this is going to have a positive exponent. If the number, when I convert to scientific notation, is smaller than 5, like in this case here, then my exponent is going to have a negative number. Okay, so that may be one way to kind of help you remember that. And I only say that because every year I have students that get confused about when they're putting negative signs and when they're putting positive signs on the scientific notation. So just talking about it different ways to maybe help you, if you're confused about that, understand what the sign should be on your exponent. Any questions about scientific notation? Like I said, you should have already seen it before. You just may be a little rusty on it. So go online if you need some more practice with that. And we'll do a few practice problems in the book in just a second as well. Well, you know what? We'll do it right now. How about that? Example 1.6 on page 14 says, convert 610,000 to scientific notation. But it also says, so that it has 4 significant figures. So convert this to scientific notation with 4 sig figs. All right. So if I'm converting it to scientific notation, I'm going to write down 6.1. We'll figure out the significant figures in just a second, but let's just convert it to scientific notation first. 6.1 times 10. If I'm putting my decimal place here, then I took this decimal place. I took the decimal place here, right? Because there's a decimal place at the end of this number, and understood decimal place there. And I moved it 1, 2, 3, 4, 5 places to the left. All right, so then this needs to have a 10 to the, it needs to have a 5 as the power on the 10 to the 5th power. I counted that kind of wrong. I mean, it was kind of weird, but let me just show you that again. So I went the decimal place here, 1, 2, 3, 4, 5. There we go. All right, 6.1 times 10 to the 5th power. Now we need to worry about the significant figures. Does that number have 4 significant figures? It has how many? It only has 2, because you're just looking at this portion of the number, the portion in front of the times 10 to the 5, okay? It only has 2 significant figures, so we need to pad this with zeros at the end. Now we've got 4 significant figures. Does that make sense to everybody? Any questions about that? Nope. Okay. Let's do the next one. The next one says convert. It's like we got 5 zeros after the decimal place. 4, 5, 6 in the scientific notation. All right. So we're going to write down 4. This time it doesn't tell us how many significant figures, so we're just going to write it like that. 4.56 times 10. And so since this number here is smaller than this number here, then am I going to have a positive or a negative sign on my exponent? Negative sign, right? 4.56 times 10 to the negative. So we moved our decimal place to right after the 4. So we count over 1, 2, 3, 4, 5, 6. 10 to the negative 6. Give you guys a minute to write this down so I can eat a chicken nugget. Off camera. So now we're going the opposite direction. And they said, take this number that's in scientific notation and convert it into decimal notation. So with this one here, it's a negative number on the exponent. So we know that the final number is going to be smaller than that. So that means we're going to move our decimal place to the left. So it should be it should be 11 zeros. 4, 5, 6, 7, 8, 9, 10, 11. And so just to verify that, I'm going to count from here, where the decimal place is right after the 8, and make sure that I jump 12 places before I get to the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's correct. All right. And then one more time going from scientific notation to decimal. 3.4 times 10 to the 9th power. 3.4 times 10 to the 9th power. So our final number is going to be bigger because the exponent is positive. So it's going to be 3, 4, should be 8 zeros. So see if that's correct. The decimal place here should move 9 places to get all the way to the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right. It's your last chance to ask me about scientific notation if there's something that's still confusing about it. Because we're just, at this point, we're just going to move on and assume that you've got scientific notation down. So any questions? Yes?
So just like to clarify, so when, like, if the 610,000 example that you did, so if, like, it needs a certain number of significant figures, we just add 0 to whatever?
You just add zeros because in scientific notation, any 0 to the right of the decimal place is going to become significant, right? So you just add that many zeros until you get the correct number of significant figures. Good question. Anybody have anything else? All right, let's talk about derived units very quickly. And a derived unit is just a unit that is derived from other units. So for example, if I were to say 1.2 meters times 1.2 meters times 1.2 meters. I punch that in my calculator and I get 1.728, and my derived unit, because it's m times m times m, would be meters cubed. All right? And so this is, you know, I told you last week, think about your units as algebraic variables. This is the same thing we did in algebra, right? If you had something like 2a times 3a times 4a, right? We would multiply the coefficients in front of the variables. 2 times 3 is 6, times 4 is 24. We multiply those together, and then for a times a, we would say that's a cubed. So your units of measurement work the same way when you multiply them together or divide them, right? They work just like algebraic variables do. All right, is this answer correct? It is not. We're multiplying, so we need to worry about precision or significant figures. Significant figures. We need to have two significant figures because that was the least amount of significant figures in these. In this case, they all happen to have two significant figures. But we basically need to round our answer so that it only has two significant figures. So our final answer would be 1.7 meters cubed. Everybody clear? Makes sense? All right, so those are derived units. Speaking of cubic units, this is something that you need to memorize because we talk about volume a lot in here. So memorize 1 centimeter cubed, or 1 cubic centimeter, is equal to 1 milliliter. All right, so that this graduated cylinder, it's in milliliters. This beaker is in milliliters. So milliliters is usually what we use for volume, but this you should know, right? Just like I expect you to know that there are 100 centimeters in a meter, I expect you to know that 1 centimeter cubed equals 1 milliliter. All right, because we'll use that conversion relationship in some problems, and that will pop up from time to time. Not a lot. We won't use it a lot, but we will. It will pop up from time to time throughout the year. All right, so memorize that conversion relationship there. So if you've got 20 milliliters, that means you've got 20 cubic centimeters. Or if you've heard cc's, right? Like in the medical field, 20 cc's, that's cubic centimeters. So 20 milliliters, those are all the same. All right? Any questions? I just realized that the twins don't have on the shirts that say, but you guys have the, why is that?
Oh.
Explain.
We were in government class.
Government class? Okay.
And she's on Zoom. So
I got you. All right, cool. That's pretty cool. Is that a sticker or is it actually?
Yeah,
it's a sticker. Okay, all right, gotcha. Okay, and that reminds me, I did not take roll. So let me make sure everybody's here. I saw Cruz. I saw Nathan. I saw Jenna. Jed's here, Jerry and Joey, Austin. Is that you back there, Austin? There's Austin. Elizabeth is here. Logan, I saw Logan. There you are. Lily is here. Isabella's here. Michaela's here. Aria Nell. Did I say it right?
Mm-hmm.
Woo! All right, Aria Nell's here. I literally practiced that. So, and then Katie. Right? All right. Cool. Everybody's here. Now, will I remember that without looking at my phonetically spelled out? I don't know. I'm working on it though. All right. So, graduated cylinders. One of the devices, measuring devices we're going to use today is a graduated cylinder, right? So, graduated cylinder looks like this. It's got, the measuring lines on here, something like that, whatever. And so, let's just say we had this graduated cylinder here. And we'll say that this is 20 milliliters, this is 30 milliliters, and this is 40 milliliters. All right? And, let's do it a little bit more. Let's do this as, I've already done it wrong. Because I want to ask you guys about precision. So let's do, that is not drawn accurately. So I'm gonna. It's a nice thing about these whiteboards. You can do stuff like this. And I'll draw my 20 milliliter line there. Okay, so this is actually 20 milliliters. So we put some liquid in there, and what you find is that the liquid, let's say it goes up to here. The liquid is going to do something like this, right? Where it curves up on the edges of the measuring device because the liquid is adhering to the sides of the container that it's in, right? So you have this curve that's just naturally going to happen. And we call this curve the meniscus. All right? And so what you need to be aware of when we're measuring something in a device like that, when we're measuring liquids, measure from bottom of meniscus. So in this case, our measurement is going to be, because the bottom is right here at 45, our measurement is going to be 45 milliliters. Okay? Now here's my other question. Our device is accurate to what? Or precise to what? Each individual tick mark on this drawing here represents how many milliliters?
10.
No, each individual tick mark. So each of these individuals, this big one's 10, right? But we've got little ones in between it that represent 1 milliliter, right? So the smallest division with these tick marks is 1 milliliter. All right, so our device is precise to 1 milliliter. So did I write down my measurement of 45 milliliters correctly? I didn't, right? I need to write it down as 45.0 milliliters. So that tells whoever's looking at my measurement that my instrument is precise to that place in the number. I'm just going to kind of keep reinforcing these things until you get it down. All right? So always measure it. Use the bottom of the meniscus as your measuring point when you're measuring liquids like that. All right, let's do example 1.7 and 1.8. And so we can do some practice converting between volume units. And so they say the volume of a box was measured to be 3245 centimeters cubed. 3,245 centimeters cubed. And they want to know the volume in liters. So what is the volume? Let me say in liters. Liters equals what? So what is the number of liters equal for this? Well, we started off with centimeters cubed, and we want to get the liters. So what are we going to use to get the liters? What conversion relationship? We don't have a direct conversion relationship from centimeters cubed to liters. And then from milliliters, we go to liters, right? So we're going to convert twice. Good. So you're Joey? Okay, Joey. Did I spell that right? E-I, okay. It's so cool, I can't even spell it correctly. All right, J-O-E-I. All right. So first we go to milliliters, and then from milliliters we convert to liters. So 3,245 centimeters cubed, 1 centimeter cubed equals 1 milliliter. So we can just write this down as 3,245 milliliters, right? No need to really convert. You just swap the unit out. Now we need to take milliliters and convert that to liters. So we remember then that 1 liter is equal to 1,000 milliliters. So that way our milliliters will cancel out. And that means that our final answer is 3.245 milliliters. Any questions about that?
Wouldn't it be 3.2.45 liters instead of milliliters?
Did I write milliliters? Oh, good catch. Man, it's too bad I just gave you an extra point. Good catch. Yep. 3.245 liters. We were converting to liters. Thank you. Otherwise, I'd have had to take the video and go in there and override it and say, Mr. Walker made a mistake. And yeah, so you just saved me a bunch of time. Thank you. but you weren't sitting in this seat, so I'm a little, but you're a twin of the person sitting in this seat, so now it makes sense. All right, I got it. That seat's still the key to correcting the teacher, I'm telling you. All right, the volume of a certain refrigerator is 2.8. Any questions, just real quick? Nothing? Everybody got that? All right. This one's a little bit harder. 2.88 meters cubed. The volume of a certain refrigerator is 2.88 meters cubed. 2.88 meters cubed. All right, and they say convert that to liters. All right, convert that to liters. So what we've got to do with this one first then is convert meters cubed to centimeters cubed, and then go from centimeters cubed to milliliters, and then go from milliliters to liters. Right? Does everybody follow that path? So we'll go from meters cubed to centimeters cubed, and then from centimeters cubed to milliliters, and then from milliliters to liters. And that'll give us our final answer, right? So really 3 different conversions are happening here. The hard one, though, is the first one, meters cubed to centimeters cubed. You may be tempted to say 2.88 meters cubed times, we know 100 centimeters equals 1 meter. And so maybe you're tempted to go 100 centimeters cubed is equal to 1 meter cubed. And that would be incorrect. All right, really, there's a simple little change you have to make in order to get that right. You could simply say this, all of that cubed over all of that cubed. Now we're correct. All right, but this is the way that I like to do it. Just because it's easier for me to see it very clearly spelled out and punch it in my calculator, is we know that's true, 100 centimeters over 1 meter, and so if we do that 3 times, then I'm going to have 3 meter units on the bottom here that'll cancel out with that. And I'm going to be left, hey Joe, I'm going to be left with centimeters cubed at the top, okay? So if I punch that in my calculator, let me erase my graduated cylinder here. If I punch that in my calculator, then I've got 2880000. Is that right? Centimeters cubed. 4 zeros. Yep. 288 centimeters cubed. I started with 3 significant figures. I have 3 significant figures here, so we're good as far as the sig figs go. And so now I know that I can rewrite that answer in milliliters, because 1 centimeter cubed equals 1 milliliter. So this is the same as 2,880,000 milliliters. And so that's the number that I need to finally convert to meters. And so the way that I would do that is I would say that is 1 liter equals 1,000 milliliters. And so our final answer is going to be 2,880 liters. That's a comma, not a period. Everybody follow that?
You lost me after we figured out the first thing.
The first one? Okay. So, you good? So, did this one make sense?
Yes.
All right. So, we could write it down. This is what we know. We know that we're going to convert cubic centimeters to milliliters, and we know that this many centimeters cubed, if we actually were to write it out, we would say multiply that times 1 milliliter over 1 centimeter cubed, right? And we convert that, and that's going to give us this number.
Okay.
All right, so that's this number converted to milliliters. All right, and then I took that number and I converted that number to liters by multiplying it times 1 liter over 1,000 milliliter. So, I mean, kind of the whole thing from beginning to end was I did 2.88 meters cubed times 100 centimeters cubed over 1 meter cubed times 1 milliliter over 1 centimeter cubed times that last thing, 1 liter over 1,000 milliliters. That was all, those were the conversion steps that we did to finally get to 2,880 liters. Because if we punch this in, our units will all cancel out. Meters cubed cancels out with the meters cubed there. Centimeters cubed cancels out with centimeters cubed there. Milliliters cancels out with milliliters there, and we're left with liters. But a couple of different steps. Did that help? Okay. Anybody else? All right. So we're moving on. Let's talk about. All right. Let me ask you a question. Let's see who can remember this from last week. Matter. What was our definition of matter?
Anything that takes up space.
It takes up space and has mass, right? So anything that takes up space and has mass, right? So since you almost got us there, Kane gets that, but then Jerry came to your rescue and finished it up. Did I spell that one right? Okay. And I spelled Caden right? All right. So it's whatever takes up space, something that takes up space and has mass. Now we've looked at all these measurements for how to measure space, right? How long is something? What's the volume of something? That all has to do with space. Now let's talk about mass. We need to discuss mass because matter has mass and takes up space. So I want to make sure you've probably seen this somewhere in your academic career already, but I want to make sure that you understand the difference between weight and mass, right? So weight is a measure of how strongly gravity pulls on an object. All right? That's weight. Mass is a measure of how much matter is in an object. Once you write that down, I'll steal another bite of chicken nugget. Which are really cold at this point.
You're still good.
They are still good. They're just not really crunchy anymore. All right, so weight, the reason weight is a measure of how strongly gravity pulls on an object, that's why I would weigh more here than I would weigh on the moon, all right? Because the gravitational pull of the moon would be less than the gravitational pull on Earth, and so my weight's going to vary between here and the moon. But since mass is how much matter is in an object, if I go to the moon, I still have the same amount of matter, and so my mass would remain the same. So it's important that you recognize the difference between those two, and mass is what we're going to be focused on here in chemistry. And that's as we're doing our labs, that's the measurement that we're going to take. All right, so let's do example 1.9 and do, which I think is just a conversion problem using, it has to do with mass. And it's, again, this is a two-step conversion, so that's good. We'll see that one more time. Multiple steps to convert from one unit to another. So they give us the measurement in kilograms. They want us to find this mass measurement in milligrams. Mass of a can of soup is 0.490 kilograms. What is its mass in milligrams? And so there's two conversion relationships we're going to need for this. One is we know that, so in a problem like this, you're converting from one unit to the other, but both units have the same base unit, right? What would our base unit be in these units? Grams, right? A gram is our base unit. And by the way, just as a point of reference, a paper clip weighs about a gram, All right, just if you're trying, or that's the mass. I'm sorry, the mass of a paperclip is 1 gram. So if you're trying to figure out, just as a frame of reference, how much is a gram? So what we want to do is, if we're going to go from kilograms to milligrams, we'll go from kilograms to our base unit, grams, and then we'll go from our base unit to milligrams. All right, so there's in order to do that, we need to remember that 1,000 grams equals 1 kilogram, and that 1,000 milligrams equals 1 gram. This is back to the prefixes. I said the 3 prefixes that you needed to memorize. You should know that if you know those prefixes. Any questions about that? All right, so as long as we have those conversion relationships, we can do our problem. So let's do it like this. So first we're going to go from kilograms to gram, right? And so we put grams on top, because that's what we want to end with. And we put kilograms on the bottom. So we know that works out correctly because our kilograms cancel out and we're left with grams. And then we need to go from grams to milligrams. So we use this conversion relationship there. Since we want to end up with milligrams, we put that on top and we put grams on the bottom. And so the grams cancel out. And so our final answer is 490,000 milligrams. I think I did that right. 490,000 milligrams. Yep. Okay. Is that the correct answer?
No,
It's not. Why?
because it's not the same significant figure.
That's right. We need how many significant figures based on our original number? 3, and we only have, how many is that? 2, right? So we need to change it. This is scientific notation to the rescue, right? So we write it as 4.90. So now we've got 3 significant figures. And we're going to multiply that times 10 to the 1, 2, 3, 4, 5. 10 to the 5 milligrams. And that's the correct final answer. Any questions about that? All right. I'm not going to write anything down for it, but remember I told you last week that even though between English and metric units, they're usually different when you look at mass, when you look at distance, volume and things like that. But then whenever you look at time, they use the same unit. And the base unit generally for time is seconds. So just an FYI there, but nothing really for me to write down as far as that goes. I want to talk about density. That's our last topic today, and that's what our lab has to do with. So density, I guess I should go ahead and write down a definition of that. Density by definition is a measure of how tightly packed matter is in a substance. So some substances, the matter's spread out, right? Other substances, it's really compact. It's tightly compacted together. And so for the ones where the matter is more compact, it's said to be more dense, okay? So that's what we mean when we're talking about density. And we actually have a mathematical formula for that. And the mathematical formula is density equals mass over volume. Okay? And so for density, we use the Greek letter rho. All right, that's not a P, that's the Greek letter rho, which kind of looks like a curvy, letter P. So rho, like this would be a P, right? And that's a rho, just kind of curved a little bit. Density is equal to mass. This is the mass. Mass is this one on top, and volume is this one on bottom. All right. Make sure you know that formula. Memorize that. That'll be on your quiz next week, and it'll be on the test, so make sure you know that. And so just as a way for you to sort of think about density, when you talk about something being more dense, one of the things that I like to think about is, like in the scripture, it talks about unleavened bread, right? Like when the Jews had the Passover feast, they were supposed to eat unleavened bread with it. Bread with what is leaven? Yeast, right? No yeast in it. So nothing in it that's going to cause the dough to rise and swell up. And so unleavened bread is more dense than bread with yeast in it, right? If you get that nice fluffy package of Sunbeam or Nature Valley or whatever, in the store, it's nice and fluffy and squishy. But if you get bread without any leaven in it, it hardly squishes at all because everything's more tightly compacted together, right? And you can have a piece of unleavened bread and it would feel as heavy as like several pieces of leavened bread would, right? Because the matter is more tightly packed together in the unleavened bread because the yeast fills the other one with basically carbon dioxide and it puffs it up, right? Makes it bigger. And so that's a good way to me to kind of mentally think about that. If just a visual picture of something that's more dense than something else, and will help you just kind of have a frame of reference there as far as what I mean when I say something is, one substance is more dense than the other substance. But I wanted to share, like I said, the yeast, the leaven causes things to puff up. So there's a verse that I like in 1 Corinthians 8:1, and it says this: knowledge puffs up. So knowledge is like yeast all by itself, right? You guys are in chemistry class, and I'm trying to give you guys all this knowledge, right? But if you ever met somebody that they're so smart, and they want everybody to know that they're that smart? You ever met someone like that? It's like, whatever you say, I'm gonna blow you out of the water about how much I know. Why is that? Well, because all they have is knowledge. And that's what the scripture says. Knowledge is like that leaven in the bread. Knowledge puffs you up, right? It makes you become inflated. It makes you become proud. But the latter half of that verse says, knowledge puffs up, but love edifies. So the way you guys are going to take any kind of knowledge, including this chemistry knowledge, and take it away and it be useful, is if that knowledge is always balanced with love. What love does is love builds up other people. So someone that's really smart, but then is kind to others and turns around and is trying to teach them and help them, that's somebody whose knowledge is balanced with love. So knowledge all by itself puffs up, makes you less dense, if you but love edifies. Love will build up others and help others. So anyway, I like that verse. I wanted to share that. All right, so does everybody kind of understand, though, the concept behind density? Does that make sense? How tightly matter is packed together. So let's do an example so that we can use our formula, all right? Example 1.10 on page 23. And it says the mass of a gold object is 38.6 kilograms. So it gives us the mass is equal to 38.6 kilograms. And it says that the volume is 2.00 liters. Volume equals 2.00 liters. What is the density of the object in grams per milliliter? So they want us to find the density in grams per milliliter. All right, so you know how it is. They can't just give you like a straightforward, you plug it in and you're done. They always throw you a slight curve, right? So what's the curveball here? And that prevents us from just taking the numbers directly and plugging them in.
We have to transfer the volume.
We have to convert them first to a different unit, right? So you said it much more like a question, but I'm going to give you the credit anyway. Next time I want boldness, okay? Be assertive, man, all right? All right, good job, Nathan. So we're going to convert it over to the correct unit first, right? They want it in grams per milliliter, so this needs to be converted to grams, right? And this is going to have to be converted to milliliters before we can plug it into our equation, all right? So converting this to kilograms, once you guys get good at this, you can probably just move the decimal place around, because I can just look at this and say, okay, it's going to be 0.0386 grams, all right? I'm moving my decimal place 3 places to the left. But let's plug it in until you get good at it so that we don't make any mistakes. So 1,000 grams equals 1 kilogram. And the reason that I knew the decimal place was going to, and see, I told you until you got good at it, what did I do? I did it wrong. I moved my decimal place the wrong way. 38,600. Because what you'll see is if you're multiplying times 1,000, you'll know that you got to move the decimal place 3 places to the right. Right? So 38,600 grams is how many grams we've got. We have to take a quick look and make sure that our significant figures are okay, and we're all right. Right? We started with 3, we ended with 3, so we're good there. What about volume? We're converting volume from 2 liters to milliliters. So we do 2.00 liters, and we convert that to milliliters. So 1,000 milliliters equals 1 liter, and so we have 2,000. Move your decimal place again 3 places to the right, milliliters. Now, is that measurement correct? That one is not. No. And it's not correct because we don't have the correct number of significant figures. So how did we learn to represent a number like that with the correct number of significant figures? Scientific notation, right? Use scientific notation. So if I write this as, I need 3 significant figures, so if I rewrite this as 2.00 times 10 to the 3rd power milliliters, now I've got the correct number of significant figures. All right, are we ready now to just plug our numbers in? Yeah, we are, right? We've got them in grams per milliliter. So now we can just say that density is equal to the mass, 38,600 grams, over 2.00 times 10 to the 3rd milliliters. And so that I cannot do in my head. And so we're going to see 386 divided by 19.3. So net. Oh, he got away. Bummer. 19.3 grams per milliliter. All right, so that's the density that we calculated for gold in this particular problem. We had a gold object, and we calculated it to have that density. And so as it turns out, generally speaking, you can identify a substance by its density. This is the way that they used to verify that a substance was indeed pure gold. They would take the mass of the substance and they would divide it by the volume of the substance, and if it turned out to be 19.3, then they knew they were dealing with pure gold. So density, for the most part, is usually a unique number for each individual substance. All right, any questions about how we did that? Let's do one more, and then we'll do our lab. Example 1.11, and here they ask us here we get to use a little bit of algebra. The mass of a sample of iron pyrite is 1.32 kilograms. Mass is 1.32 kilograms, and they want to know what's the volume if the density of iron pyrite is 4.9 grams per milliliter. Density is 4.9 grams per milliliter. All right, so we're trying to find volume. So in this case, they gave us mass, right? That portion of our equation. They gave us density, that portion of our equation, and they didn't give us V. So the first thing that we want to do here is we want to take our equation and rearrange it algebraically so that we solve for V. Right? V equals what? And so what we come up with is V, and this is something that you've got to make sure that you know how to do this. This is basic algebra stuff, but if this is still fuzzy, this kind of manipulation of an algebraic equation is not going away in this class. All right. So if you're still struggling with these kind of simple rearranging of problems, and I have kids every year that, like, we're at the very end of the year almost, and they're still messing these things up. Go ahead and get that down now. Do the, like I said, Khan Academy, or pull out your old math book and figure that out. All right. But if we rearrange this, it would be V equals M over rho. Okay. And I'm just going to go through the steps real quick, just in case it's still fuzzy to some of you guys. How would we get that from this? So what we would say is we got rho equals M over V. We want to solve for V. We want to get V on one side by itself. So what we do is we multiply both sides by V, because remember in algebra, whatever you do to one side of the equation, you have to do it to the other side of the equation, right? So this is going to cancel out our V's over here. And so we're left on this side with V times rho equals M. And we want to get V all by itself, so we divide both sides by rho. Right? And the rho's cancel out over here, so our final equation is V equals M over rho. And that's what we got right here. So make sure that you can rearrange these simple equations like that to solve for a different variable. All right? Any questions about how I got that? All right? Are we ready now to plug it in our equation and solve for volume?
Yes.
We have a yes? You're like, well, obviously, Mr. Walker, since you're not going ahead and doing it, the answer must be no, right? What do you think? Are we ready?
Mm-mm.
We're not. Why not?
Because when 1.32 kilograms needs to be grams.
Right. Yeah, we've got a unit here that has grams in it and a unit here that has kilograms in it.
Mm-hmm.
So you got to make sure that all of your units of measurement match up before you start plugging it in an equation like this. So we've got two options, right? We could either convert this mass unit to grams to match this mass unit, or we could take grams here and convert it to kilograms. But I think it's easier to convert this to grams, so that's the route that I would probably go, right? So, Aria now?
Yes.
Did I say it right?
Mm-hmm.
It's not area now, it's Aria now.
Mhm.
Okay, all right. And now can I spell it?
One more L.
One more L. I started to ask, was it two L's? Okay, cool. All right, very good. So let's convert this to grams real quick. 1.32 kilograms. I didn't want to do equals. I wanted to do that. 1,000 grams over 1 kilogram. So it's 1,320 grams, right? Is what that's equal to. So then we can plug that in our equation. Volume equals 1,320 grams, and we're okay here because it has the same number of significant figures, so we're good with that. Over the density, which is 4.9 grams over milliliters. So we get a final answer in this problem of 270. Well, let me punch that in real quick to see if it works out that way exactly. 1320, and it doesn't. I remember from the last class. 4.9. So we actually come up with a number. I'm just going to round this to 2 decimal places. 269.39 milliliters. So 2 things I want to make sure that you're comfortable with here. One, do we have the right number of significant figures? And the answer is no, right? Because our smallest amount of significant figures was in this measurement before, and it only has 2 significant figures. So we've got to round this guy to 2 significant figures. So our actual answer would be that. You guys see how we had to do that? We have to round it to where we only have 2 significant figures. So it would be rounded to that. And that's because the least amount of significant figures we had in any of our original measurements was 2. So we have to round it to that. And the other thing that I want to make sure you understand is how we got milliliters as our unit there. And again, this is kind of an algebra thing. Maybe even really, you probably saw this before algebra, but algebra was when you started doing it with variables, right? So remember, if you think about your units as variables, our units here are grams over grams per milliliter, all right? So it's like that. And when you've got a fraction, on the bottom of another fraction, then that's the same as taking this number here and multiplying it times the reciprocal, the fraction that's on the bottom. Do you guys remember that? Right? So this is the same as grams times milliliters over grams. The reciprocal is where you flip it. Right? You flip this fraction. All right? This is an over and understood one. Right? So now the grams cancel out and we're left with just milliliters. And so that's how we got the unit of milliliters. All right? It should have been obvious to us because gram is a mass unit and milliliters a volume unit. So it should have been obvious to it that we were going to end up with milliliters since we solved for volume. But you should be able to do that. You should be able to cancel those units out and figure out what the final unit would be. Because that's not going to go away either. So make sure that you understand that. And again, that's just algebra. If you think of your units as your variables in algebra, and you're good at that, then you should be able to do your units as well. All right, any questions before we go to the lab? All right, excellent. We are doing lab 1.3 on page 25. All right, so there's 5 basic sections that we need to include in our labs. And the lab rubric, like I said, it spells those out and tells you how many points each of those sections are worth, and kind of like the pieces within those sections, how many points they're worth. So here's the thing with your lab. This is your easiest way in this class to keep your grade high. All right? Labs count 30% of your grade, and there's no reason that anybody in here can't make 100 on every single lab. As long as you cover the stuff that's in that rubric. All right? And I'm not asking you to kill yourself, on writing some 5-page lab report, but I do want enough detail. Here's the goal with your lab report. I should be able to take your lab report in the future, not have the book, and repeat the lab that you did. Okay, so your steps should be clear enough that I understand how to do the lab without having the book. So think about that when you're writing down like the steps to your lab and the things that you did. That should be understandable without me having the book handy. Okay, but your lab report should basically have 5 sections. The first is your introduction. All right, if you look on the back of the page that I gave you, it breaks down each of those 5 sections and tells you what should be in them, right? So your introduction, in essence, I'm looking for, you're introducing me to the lab that we're doing, right? Why we're doing this lab. And then, very critical in this portion, and the rubric shows this as well, I'm looking for your hypothesis as to what's going to happen when you perform the lab, right? Your best educated guess on what you think is going to happen. All right, in this lab, for example, we're going to be checking the density of water, the density of oil, and we're going to mix those together. And so, your hypothesis might be, I think the oil is going to be more dense than the water, or vice versa. When we mix them together, I think one's going to float on top of the other, or something like that. It's your educated guess as far as what's going to happen. All right. Next, what's the next section after introduction?
Procedures.
Your procedures. All right, I want your lab report to have these sections here clearly marked, right, and separated out. So I want to see headers that says introduction, and then see your introduction information, and the header that says procedures and shows your procedures information. Okay, I'm actually going to email out a sample lab report from last year where just somebody that had all that stuff clearly laid out, so you can see what one looks like. Okay, so your procedures. This is the stuff that you did to actually perform your lab. It's not any of your measurements that you took while you were doing the lab. It's not any of the calculations with numbers in there. This is just the steps that you had to take to perform the lab. So it's the same stuff that's in your book, right? You know how your book's got it listed out there. What page is it on again? 25. So those steps 1 through, all the way through 19 that they have on there, that would be the procedures of the lab. Now that includes a little more detail for this first one than I expect you to have in your lab, because they're telling us how to do things like use our mass scale. And you can assume that someone, take your mass scale out and do this and that. You can assume that they know how to use the mass scale. You don't have to be quite as wordy as they were here. But the point is, I should be able to follow your procedures without having the book and perform the lab. Now, one thing that this section also should include is your formulas, okay? So steps to do lab, needed formulas. Right, so this is a density lab, and so this is the place that you would include the formula rho equals mass over volume. All right, None of the numbers here that you use to calculate the density, that's going to go in the next section, but the procedures should include the formulas. All right. Next we have, what is it, observations? Right, so observations, that's the actual measurements that you take. You know, if you mix something together and it changed color, right, that's an observation. The things that you observe happening as you do the lab. Any calculations, so this is, you know, things observed, calculations are going to go there. So that's where you actually plug in your numbers and you actually calculate the density, right? Where you record your measurements, right? We looked at the mass of the graduated cylinder with the water in it and it had this value. That's all going to go here in your observations, okay? Because that's the stuff that you observed as you perform the steps. Any questions so far? All right, and so is that the section? Can I see the rubric real quick? I gave another teacher my copy, so I've got to make me another copy. Okay, no. So the thing I wanted to point out is in the next section. So the next section is conclusion. Again, I want these sections clearly marked. I don't care if you type out your lab report or if you write it by hand. Either's fine with me, except for the diagram. You need to draw your diagram. But again, I just want to make sure these sections here are clearly defined. All right. So your conclusion, that's going to be, you know, what was your final conclusion with the whole thing? You know, we determined that, you know, Elizabeth's hair was more dense than RNL's. I don't know. You know, whatever our experiment was, that's our conclusion. Think that's true? No, probably the other way around, right? Yours is a little fluffier. A little more air in there. So the conclusion has to do with what was it that you discovered, right? What was the conclusion that you came to from the lab? But something that's very important that I don't want you to overlook in the conclusion is your experimental error, right? So make sure that you include your experimental error here. How many points does it say that counts on the rubric? I think it's like 10. It's the last one, I believe, last item under the conclusion. Is that right? So you just lost 10 points, and the best you can make on your lab is 90 because you didn't put experimental error in there. And experimental error is simply just saying the one possible place of experimental error during this lab is, you know, we did this. Like one of the things that we're going to see whenever we add water to our graduated cylinder and we take the mass of that is that the water, unless you're very, 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 very careful, you know, the water's going to splatter on the outside of the container. You'll have some that maybe adheres to the top of the container, and so you're going to have excess water on there that's adding to the overall mass that was unintended, right? So things like that can introduce experimental error. Every experiment has experimental error. So just think about some way that you may have introduced error, right? This is not about right or wrong, but it's about you giving me a thoughtful answer, right? Saying what you think and making sure that you include all these parts. So as long as you list experimental error, you're going to get 10 points of credit for that, right? But if you leave it off, you lose 10 points. So I don't want you to do that. I don't want you to lose those points. And then the last section is the diagram. And the diagram is simply a hand-drawn picture of some portion of the lab, right? So when we're done with this one here, we're going to pour the oil and the water together, and we're going to see how they separate. So you could give me a drawing of your beaker, right, with the oil and the water separated. That would be a sufficient diagram for this particular lab. But just make sure you label the different parts, right? You should, if you got oil and water in here, you should have the oil clearly defined in your drawing as well as the water, right? I should be able to know what I'm looking at, what each part represents. All right? And the diagram, again, I think that's like another 10 points for that. So make sure you don't leave that off, or it's going to count a lot against you. As long as you have all this stuff in here, guys, you know, and I can tell that you actually spend a little time doing it, you know, I'm going to give you the bare minimum, and I don't care about this at all. If I see that, you're going to get some points deducted just because I need more detail, right? But as long as I can see that you're doing your best to represent what you did in the lab, and you've got a diagram, and you've got your experimental error, you're going to get 100 points every time. All right, and it's really hard to make a bad grade in this class if you got a bunch of labs that were hundreds, right, or 90s.